Now, if we continue from the previous page with all the current going around this RL circuit, then what will happen if you suddenly change the switch from A to B, right? Okay, now if you change the switch from A to B, this EMF device is now disconnected from the circuit. So therefore, because there is no more source of this electric power, the electric energy will be dissipated on this resistor. So therefore, the current will decrease. Okay, but then again, this inductor does not like that change. So therefore, the current cannot quickly decrease from a large value to 0, but it will only do so very slowly. Okay, this is the situation we are going to calculate. And in this case, actually, if you think about it again using the same loop rule, try to add all the potential differences, and then actually the direction of the current is still the same. So going around the loop, originally in the previous page, we had this VEMF here, okay, and VEMF here. Only that part has disappeared, okay. So therefore, we actually have a similar form. And since this equation looks similar, the solution also has to look similar, okay. And again, this is the final solution we get. And again, let's try to make sense. In the beginning, when all the currents were flowing without much change, I said that in that case, inductor is just like any conducting wire. So therefore, initially at time t equals 0 in this case, the original amount of current was simply VEMF divided by R. So therefore, if you insert t equals 0, exponential of 0 is 1. So therefore, it makes sense. And then after switching this from A to B, if you wait long enough time, then of course all the current will be gone. So therefore, current will become 0. So in that case, we have to insert here infinity. So if you insert time equals infinity, exponential of minus infinity is of course 0. So therefore, finally, all becomes 0. So you can again use the graph to represent it. So it's going down slowly like this, and then finally becomes 0. So basically, it follows the so-called exponential decay, which is exponential of minus t. Okay. So as a summary, the key lesson of resistor-inductor circuit is that the current through an inductor cannot change abruptly. And this is similar to the behavior of charges in the resistor-capacitor circuit. So therefore, the current in the RL circuit and charges in the RC circuit cannot change abruptly, and then it takes time for them to become saturated during the charging process or become 0 during the discharging process. Okay. Okay, and in this slide, we will study how energy is stored in an inductor. Okay, and before doing that, let me remind you of the case of a capacitor. You know, in capacitor, we stored electric charges, and the electric field of these charges stored energy, right? Okay, I hope you remember that. And then we just learned that the current in inductor behaves like charges in capacitor. So therefore, we can also say that the current stores energy in an inductor. But soon we will actually see it is the magnetic field that stores energy in an inductor, just like electric field stores energy in a capacitor. Okay, so let's try to calculate it. So how do we do that? We will use the equation that we have seen before. So in this circuit where this EMF device delivers energy to the resistor and an inductor, the same equation we used to calculate the current, right? Okay, so starting from here, let's multiply current on both sides, and this is what you get. Okay, and then here on the left part, do you remember what is this current multiplied by the potential? I hope you remember it. It is actually the power. Power was of course, the time rate of change of energy, or time derivative of energy, right? Okay. So therefore, this left term represents the rate at which the EMF device delivers energy to the rest of the circuit. How does it deliver the energy? By moving charges through the circuit. Okay, that is actually the current. Okay, and this second term, I square R, what is this? This is actually the rate at which the energy dissipates or disappears or appears as a thermal energy in the resistor. Okay, so which means is that when the current flows through this resistor, the resistor becomes very hot. So the electrical energy changes into the thermal energy and gets lost. Okay, so therefore the final term here, which is remaining here, means the power of power which is remaining in the inductor. Okay, this is what we are interested in. Okay, so therefore this last term here is still a power. So therefore we have to use the time derivative of the energy, and with this energy we call it UB, because eventually it will be the energy of the magnetic field. Okay, and if you look at it on both sides, is shown as a derivative form, right? Okay, so here let's multiply both sides with dt, and then do the integration on both sides. Okay, and from the left side you get the total value of the magnetic energy, and on the right side, what is it? L is a constant, and if you integrate I with di, then you get half of I squared. Okay, so finally this is the energy stored in the inductor. Okay, so it looks like it is the current which stores energy. Okay, so it is actually correct to say that current stores the energy in an inductor. But now let's try to calculate the energy density from here. So how do we calculate the energy density? Energy density simply means the energy per unit volume of this coil or inductor, right? Okay, so therefore in order to consider it, let's suppose this inductor has an area A and length L. Then the volume will be simply A multiplied by the L. Okay, so energy density is now simply the energy divided by this volume, and then it's just like this. Okay, and then from here, in order to calculate further, now let's try to introduce ideal solenoid, because that's what we already know. Previously we learned that this inductance of an ideal solenoid is the length multiplied by this much. Okay, and then we also learned that the magnetic field inside ideal solenoid is like this. Okay, so these are the things we actually learned in previous pages, so please go back and check, and we will use this. So okay, let's here in this magnetic energy density, we had an inductor, so you insert this inductor, and when and then at the same time, okay, it's a current square, right? It's a current square. This current can be converted to magnetic field. So if you summarize it, this is what you get. So finally the magnetic energy density, which does not depend on the shape of the inductor, is simply magnetic field square divided by 2 mu naught. Okay, and try to compare this with the energy stored in a capacitor, and I mean the energy density in a capacitor. Here we had the half of this permittivity constant multiplied by the electric field square. Okay, so they look very similar. For the capacitor, we had the electric field square. For the inductor, we have this magnetic field square, and there's a half term because we were integrating it, and then also constants. For the electric field, we had this permittivity constant, and for the magnetic field, we had inverse of this permeability constant. Okay, So therefore, we can finally say the inductor stores energy in the form of magnetic field. Okay. Okay, so now let me summarize this lecture. So in this lecture, you have learned the Faraday's law of induction, which described how EMF was induced by a changing magnetic flux. And we also learned the Lenz's law, which explained the direction of the induced current and the negative sign in the Faraday's law. Okay. And then we also learned that this Faraday's law actually have to be reformulated using the electric field. Okay. And we also learned a device called the inductor and its inductance. And this inductor is important in electric circuits because they oppose sudden changes in current, just like capacitors oppose sudden changes in electric charges. Okay. And in using this, we learned how a current changes with time if an inductor is included in a circuit with a resistor. And finally, we learned that an inductor stores energy in the form of magnetic field. Okay. And in the next online lecture, we will study these things, which is, of course, a continuation of what we have learned in this chapter. Okay. This online lecture was particularly difficult for me because it took very long time. But if you have learned something, then I will still be happy. Okay. So please study hard, and I will see you on Thursday. Goodbye.